this video, we're going to look at sections 8.1 through 8.3. Alright, so in Chapter 8, we're finally to the part in the course where we're going to look at residual analysis. So up to this point, we've always written assumptions, line, and we've said, okay, we're going to get to these later on. Well, we're finally there. So just as an introduction, 8.1 says we're now going to learn how to check to see if those assumptions that we've stated regarding the error term. So remember here, when we learned about those assumptions earlier on, they were always in term about that error term because the error term was really the random piece. And so the four assumptions that we need to check are the errors normally distributed? Do they have mean zero? Is the variance constant? And are all pairs of error terms uncorrelated, or in other words, are they independent? So we're going to start out in section 8.2 by looking at the regression residuals. So the error term in a multiple regression model is not observable. So consider the model that we have right here. And remember that we're making the assumption here that the errors are distributed normal, 0, sigma squared. Alright, so we could take this equation and we could solve for the error term. And notice we do that by just subtracting off all of these terms on both sides, which yields the following. So what we can do is we can use the regression residuals to estimate the unknown errors. So in other words, we can't actually observe the errors, but we can observe the residuals. So we're going to use the residuals to help us learn about the errors. And so notice here, this term right here, the epsilon hat I, it has a hat. And the reason we have the hat there is because it is an estimate. In other words, the residuals are going to help us estimate error. Alright, so we have our formal definition here. The regression residual is the observed value of the dependent variable minus the predicted value. So in other words, it's how far away from whether it be a line or a surface that our estimate of, our fitted line or fitted surface and our actual observed that we saw in the sample. So it's looking at that distance. So here we've got kind of a picture of what's going on. And so notice that this is written in terms of simple linear regression, a line, but remember we know multiple regression could be a surface, it could have different shapes. So, but just for illustration here, notice that we've got our estimated model is given by the dark line. The true model is given by the gray line. So notice what we have here, these are parameters. The beta naught and the beta 1, whereas the beta hat naught and the beta hat 1, these are statistics. So this is the unknown truth. This is our estimate we found based off of our sample information. And so now looking at what some of the different pieces are, notice our residual, if right here we have some observations, the residual is going to be the difference between the observed value and the estimated model, whereas the true error is the difference between the observation and the actual model that we cannot observe. And so they've got two examples here. Now ideally what we hope is happening is we're hoping that our estimated model is close to our true model, and if that is the case, then the residual and the error will be very close to one another. So what we're going to do is we're going to use the residuals to check the regression assumptions, and this is known as performing a regression analysis, or a residual analysis, not regression analysis. So summarized up top, we've got some property of regression residuals. So the mean of the residuals will always be equal to 0. And so this property comes from the fact that the sum of the differences between the observed y values and their least squared predicted y hat values is equal to 0. And we looked at this just briefly early on, if I'm not mistaken. And so this is part of the properties of least squares predictions. And then the standard deviation of the residuals is equal to the standard deviation of the fitted regression model. And this is little s. And so we've talked about little s, way back at the beginning of the course. And so this property follows from the fact that the sum of the square residuals is equal to the SSE. Again, we've talked about this before. So, when we divide that by the degrees of freedom, it's equal to the variance of the fitted regression model s squared. And then the square root of the variance is both the standard deviation of the residuals and the standard deviation of the regression model. And so you've got your formulas here. So recall that we had this housing example from the chapter 4 notes. And just as a reminder, that example is on page 5 of the chapter 4 notes. And so we talked about this example a lot. This is the one where we had sale price, land value, improvement value, and area. And the idea was we were trying to predict the sale price based off of these three predictors. So if we look here at our SAS code, you'll notice what we've got here. Our first input is property, and that is just an identifier 1 through 20. The next one is the sale price. We then have the land value, the improvement value, and we then have the area. And this is just an error here. There's an extra space here, but SAS would read this line just fine. And then we saw previously how to run that regression model. So on the next couple pages, we've got some output. I'm just going to show you which pages I'm skipping, but we will come back to them as we need the different pieces. So the first one here, this is where we get our different predicted values. So we're going to our different estimates, not predicted values, our different estimates. So we're going to skip this page for just right now. Now let's look at this page for just a moment. This is called the output statistic page. So first of all, notice we've got a couple different things here. We've got the dependent variable. This is going to be your observed y's. So if we take just a moment, let's go back and compare this with the data that we inputted. So here is that SAS code. Notice that all of these values that we inputted, these are equal to these values here. So this is our observed y's. The next line it's going to give us, these are our predicted values. So these are our y hats. And so these are the predicted values for each of the observed values of the explanatory or the dependent variables that we had. And then another thing to note here is we do have a column for the residuals. Those are going to be the yi's minus the y hat i's. So for example, if you take the 68,900 and you subtract off 68,557, you will get the 343.2651. So that's where those differences are coming from. And then if we look down here at the bottom, notice that we've got the sum of the residuals is equal to 0. So this right here is illustrating property 1 from the previous page. And so that's this property right here, that we get the mean of the residuals is equal to 0. And then the second one we have here is, notice this is property 2. And so notice that property 2 tells us that the standard deviation of the residuals is equal to the standard deviation of the fitted regression model S. Well, let's check that. So notice the sum of the squared residuals, we get this value here, and we also find this value right here as well on page 3. And so that's really all we need to see for right now from this output. And again, we're just looking at the properties of the residuals. So we're going to move on to page 5. So on page 5, we're now going to start talking about detecting lack of fit. So the first assumption is that the expected value of the errors is equal to 0 for any given set of values of the explanatory variables. So if that model is specified incorrectly, this will not be the case. So just as a reminder, for our example that we've been looking at, we had 3 different independent variables, and let's just write them on this page so we have them. The first one is we have land value, we have improvement value, and we have area. All right, so in order to detect a model lack of fit, we look for the following. What we're going to do is we're going to plot the residuals on the vertical axis against each of the independent variables on the horizontal axis. So that's one thing we could look at. We could plot the residuals on the vertical axis against the predicted values on the horizontal axis. And no matter which one we use, in each plot we look for trends, dramatic changes in variability, and or more than 5% of the residuals that lie outside 2 standard deviations of 0. Any of these patterns indicate a problem with the model fit. So what we're going to look at first is actually the second one. So we're going to look at the plot of the residuals on the vertical axis against the predicted value on the horizontal axis. And that is given right here. So this is number 2 from up top. All right, and so again, we're going to look for trends, dramatic changes in variability, and or more than 5% of the residuals that lie outside 2s of any 0. So looking at this plot, I'm not too terribly concerned. This looks fairly random. We're not too far away from 0, or at least, 5%. So I'm not too concerned looking at this plot right here. Now let's look at the first one. We're going to move to the next page. So now looking at page 6, notice what we have now. So this is number 1 from our list before. We've got each of our independent variables, and then we've plotted them against the residual. And again, in terms of random scatter, it doesn't look bad. I don't have, that many that are, within, pardon me, that are further away than 2s away from the residual. So we're doing pretty good here. All right, so let's look at another example. So consider the tire pressure problem from the Chapter 4 notes, and this one was on page 29 of the Chapter 4 notes. So we're going to see what happens when we fit a linear model to something that's obviously quadratic. And so if you'll recall, we had this obvious quadratic relationship between pressure and mileage. So what I've got here, this is the Minitab output for that problem. And what we're going to look at on the next page is we're going to look at the residual, or those different plots. All right, so looking here on page 7, we have 2 different sets of plots, and they're in opposite order of how they are listed on our page 5. So recall on page 5, we had these 2 different ways that we were going to plot things to look for lack of model fit. And so looking at our page here, this one is the second bullet point, and this plot is going to be the first bullet point. All right, so we're looking for any kind of pattern or obvious trends. And so notice in both of these plots, we see a pattern and an obvious trend. We go up and then we go down. So in both cases, we have an obvious trend. So per page 5 that we just looked at, this suggests a problem with model fit. And this really isn't surprising because we already saw back in chapter 4 that we should be using a quadratic model for this data. So it should be no surprise if we fit this using a linear model that that's going to be a problem. All right, looking here at page 8, so we're going to look at partial regression residuals. So partial residuals measure the influence of xj on the dependent variable y after the effects of the other independent variables have been removed or accounted for. All right, so here we have our definition of what are called a set of partial regression residuals. So what we're doing here is for the jth independent variable, xj, we calculate this as follows. So notice here we've got an epsilon hat star, so we're going to use that star to help us denote that we've got a partial regression residual here. And if we look at our subscripts, what is happening here, notice that we go all the way from 1 up to j minus 1, and then we jump up to j plus 1. So notice what is happening here is this is without the beta j xj. So that's the piece that we still have. So what ends up happening is epsilon hat star is equal to the epsilon hat that we saw before plus beta hat j xj. And so if you go back and look at the previous page, the reason for that is epsilon hat has the beta j xj removed, so epsilon hat star is going to be the epsilon hat plus this term. So what this tells us is a linear pattern in this type of plot indicates that the variable would be useful in the model, and the slope is its regression coefficient. So the plot shows the strength of marginal relationships between y and xi in the full model. If the partial residual plot for xi appears flat, xi may not be needed to be included in the model. And so notice here, we've used I in this paragraph, but that could really be j as well, because j is the one that we're removing or we're looking at. So if the partial residual appears like a straight line with non-zero slope, that suggests xi should be included as a linear term, or etc. And so again, if you want to, just so this matches our notation that we have up top, you could replace all of these i's here in this paragraph with j's. Nonlinear relationships, heterogeneous variances, and outliers may also be detected in these types of plots. So again, we're going to recall that housing example from the chapter 4 notes. And so just as a reminder, again, this is on page 5 of the chapter 4 notes. Here are the partial regression residual plots. And so notice what it does here is it includes the intercept. We're not going to worry about that. We know the intercept's always going to be in the model. But for each of our independent variables, we've got land value, area, and improvement value. So all of these have a fairly linear pattern to them. And so that would suggest that these are useful in the full model. If it appears flat, none of these are terribly flat. They've all got some slope to them. That might help us make choices. But again, we would never want to just exclude a variable based solely on these plots. These are just ways for us to look at the residuals. We would still want to perform those hypothesis tests that we saw previously when we looked at this example. All right, so this concludes the section 8.1 through 8.3 notes.